In today's lesson, we're going to learn the last type of reactions with aldehyde and ketone. This is the addition-elimination reaction with 2,4-dinitrophenylhydrazine. And after learning this reaction, we're going to move on to reactions related to carboxylic acid. Let's move on to part E, addition-elimination with 2,4-dinitrophenylhydrazine. This is one of the compounds that has the longest name that you need to remember. Okay, and also you should recognize a short form is 2,4-DNP, but you should also be able to write the full name. Okay, make sure you can spell it correctly, 2,4-dinitrophenylhydrazine. Okay, so why we call this reaction addition and elimination? Okay, so here, although the mechanism is not required, but it's good to show you how it works. So it's a two-step process. In the first step, the nitrile group here got the lone pair on it. It worked as a nucleophile, so it would attach this carbon, which is slightly positively charged, and then push the electrons towards the oxygen. Okay, so this is the first reaction, addition reaction. And after the reaction, you can see elimination of water going to happen. So it will eliminate the water from here. So it will form the CN double bond in the end. Okay, so again, the whole process is not required and the product will not be required here. But this is a good way to test the presence of the carbonyl group in the compound. Okay, and after we have proved that the carbonyl is present in the sample, then we can further differentiate whether it's an aldehyde or a ketone using either Tollens reagent or other method we have mentioned before. Okay, so for this part, the most important information you need to remember is that the melting point of the crystal formed can be used to help identify which carbonyl was used. Okay, so if we measure the melting point of the crystal formed from 2,4-DNP, then we can compare the melting point with known values in the database and work out which compound is formed. Okay, so here we got some example. You can see for different compounds, they got different melting points. So you just compare it. You can look up those data in the data bank, and then you carry the experiment to measure out the melting point of your sample using this kind of machine. So how this is worked. So first you will get a small tube similar to this, and then you will add small amount of the sample into that tube, and then you will insert your tube on top of that machine, and you can then heat it up in the machine. Okay, and then you can watch the change of that sample through this part. Okay, and also it will show the temperature of the machine. And once you see the temperature that is started to melt, then you will press a button here, so it will record the first temperature. And when you see that all the sample has melted, then you will press the button again, so it will record the final temperature, and that's the final melting point, and you will get a range. And for the range, you will you will compare to the number that you look it up in the data bank. When you test aldehyde or ketone with 2,4-dinitrophenylhydrazine, the expected observation will be the green clear solution will turn to form orange precipitate. However, in reality, the precipitate will not as orange as it is shown here in the photo. So now let's watch the video that's showing the experiment of 2,4-DNP with aldehyde and ketone.
Okay, on the left here we've got the aldehyde, this is ethanol, and on the right 2,4-DNP. I'm going to add the 2,4-DNP to the aldehyde. Tip here that it is important that the 2,4-DNP is in large excess here by way of volumes. So in goes the 2,4-DNP. We're looking for the formation of a precipitate which is orange in colour. We're certainly seeing it go cloudy, which is indicative of a precipitate forming. And if we're patient, we will be able to make out eventually that we have a fine precipitate that is orange in colour. Looking more green there, but I think you can see signs of orange, and as the precipitate would fall to the bottom eventually, then we would observe it as a precipitate, a fine orange precipitate. So with the aldehyde and the ketone, we've got a positive test here with 2,4-DNP. We've got the formation of a fine orange precipitate. In this case, the reaction is ethanol plus 2,4-dinitrophenylhydrazine gives ethanol 2,4-dinitrophenylhydrazone. I'll just hold that perhaps up to the window. Not sure you can see that any better. So here on the left I have the ketone propanone, and on the right we've got the 2,4-dinitrophenylhydrazone. In it goes. I think you can see they're going cloudy, indicative of a precipitate forming. And indeed I think you can make out the colour there to be orange in colour. So we're getting a fine precipitate which is orange in colour. The propanone is reacting with the 2,4-dinitrophenylhydrazine to form propanone 2,4-dinitrophenylhydrazone. And here you see what the test tubes look like after a couple of minutes. The results of the reactions between 2,4-DNP and the aldehyde on the left and ketone on the right. We've got that precipitate described as an orange precipitate formed, which is the 2,4-dinitrophenylhydrazone of the aldehyde or ketone.
Let's move on to reactions with carboxylic acid. So as an acid, it will undergo similar reactions that we have learned last year in Unit 14. So you can refer back to Unit 14 notes for details. So first type of reaction, as an acid, it can react with some metals, some reactive metals. So again, you need to revise the reactivity series, and you know that the metal above copper, they can react with acid. Okay, so here we got example. First example, we have ethanoic acid react with magnesium, and then we're going to form this magnesium ethanoate and together with hydrogen gas produced. And secondly, we got the same acid, ethanoic acid, to react with zinc, and similarly we would have this compound formed. Okay, and also hydrogen gas produced. And make sure you balance the equation. And here, please pay attention. As a common practice, for this kind of salt, we will write the organic part in front of the inorganic metal part. Okay, so unlike the salt that we have learned last year, for example, sodium chloride or magnesium nitrate, we have magnesium, the metal at the front. But here, make sure you write the organic part first. Okay, so that's the first type of reaction, acid with metal. Let's move on to the second typical reaction with acid, that's neutralization reaction. So acid with alkalines, it would produce a salt and water. So first example, again we have ethanoic acid, and here we have the alkaline, which is sodium hydroxide. Then it will form the salt, which is the sodium ethanoate, or it commonly also referred as sodium acetate, and then water. Okay, that's one example. And second example, we have this what's called a benzoic acid. Okay, react with sodium hydroxide. So the H in the acid will be replaced by sodium ion here. Okay, so what we got should be sodium benzoate with water. Okay, so please pay attention to this part. So let me get the highlighter. Please pay attention. You can see on the benzoic acid we have the benzene ring, and here we also got a carbon. So the part I highlighted with yellow is a benzyl group. Okay, and if you remember, if we simply has a benzene ring and then we connect to something else for this part, okay, for this benzene ring only, that we would refer as the phenyl group. Okay, so don't mix these two. So for the benzyl group, it got one more carbons attached here. And here I would like to talk about more. Some student may ask, why is insoluble in water? I can see an oxygen here. The oxygen got lone pair on it. I also have oxygen here with lone pair and also a hydrogen that attached to this oxygen. So in principle, it should be able to form hydrogen bond to water molecule. So why this benzoic acid is not soluble in water? Okay, so yes, some of you have noticed that the part I highlighted in yellow here is a benzene ring. So benzene ring is nonpolar. You can see the structure if we represent it using a circle or using this 3 double bonds. You can see it's symmetrical, and also it's nonpolar. So this part is actually hydrophobic, so it doesn't like water. So due to the benzene ring here, although it can form hydrogen bond, it still cannot dissolve in water. Okay, so but if we take a look at here, take a look at the salt we formed. It's sodium benzoate. Okay, so remember last year the solubility table I asked you to remember. Remember for group 1, all the salt are soluble in water. So here we have sodium salt. So this compound should be soluble in water. So by using these special properties, we can turn an insoluble organic solvent to become a soluble organic substance. Hence, we will be able to separate this insoluble organic substance from other organic substance. Okay, so here that's the most important application you need to know. So first step, if we have a mixture of organic compounds and we only want to separate the benzoic acid, then we need to first treat it with sodium hydroxide. So after neutralization reaction, we will produce sodium benzoate, which is water soluble. So the water soluble sodium benzoate will form the aqueous solution, which gonna form different layers with other organic compounds solution. And then we can simply take those aqueous solution and then treat it with chloric acid, and then we will be able to turn it back into insoluble substance, the benzoic acid. Okay, so if we take a look at the flow chart given here, so first step, neutralization, and then after we add sodium hydroxide, neutralization would happen, and then you will get 2 layers. Down the bottom, we have the aqueous solution contain the sodium benzoate, and the rest of the organic substance will remain on top. Okay, and then after we take the aqueous solution with sodium benzoate treated with hydrochloric acid, then we can turn it back to the insoluble benzoic acid. Okay, and here this is a precipitation reaction. Some of you can recognize this reaction is a double displacement reaction. So remember last year we've learned in order for a double displacement reaction to take place, we have to fulfill one of the three criteria. So it should either form a gas or water or a precipitate. So in this case, since we form the insoluble benzoic acid, so it's going to form the precipitate. And this double displacement reaction would take place, and we can simply separate the benzoic acid by filtration. Next, we have reaction with carbonates and also reactions with hydrogen carbonates. So these two reactions are pretty similar. So after the reaction, it's going to form a salt and also carbon dioxide and water as a product. Okay, and make sure you balance the equation. And the final reaction we are going to talk about here is the reduction of carboxylic acid. Remember in the previous lesson when we talked about a reaction of alcohol, the primary alcohol can be oxidized to aldehyde, and then aldehyde can be further oxidized to carboxylic acid. So here, if we have carboxylic acid, then we can do the other way. The reaction can go from carboxylic acid to a primary alcohol. And here, please pay attention. As I have mentioned, when we do reduction for aldehyde and ketone, sodium borohydride is a less powerful reducing agent. So here, for this reaction, we can only use lithium aluminium hydride. Sodium borohydride cannot reduce carboxylic acid. It's not strong enough. Right? So we need to choose lithium aluminium hydride in dry ether, and similar to the reduction of aldehyde reaction. So here it is a two-step reaction. So we first treat it with lithium aluminium hydride in dry ether, and in the second step we're going to treat it with an acid. So after the reaction, it will go to primary alcohol. For this reaction, please pay attention. When we do reduction for carboxylic acid, it will go straight to primary alcohol. Okay, so directly gives alcohol, and no aldehyde can be given out in the process. Okay, so if we go back to here, take the summary. If we want to get aldehyde out, and we only have carboxylic acid, so how should we do that? Okay, so actually we should change this diagram a little bit, and we should connect this line. Okay, it will go directly to primary alcohol. So back to my question. If I only have carboxylic acid and I want to have aldehyde as a product, so what should I do? Okay, so the answer is I take carboxylic acid and I treat it with lithium aluminium hydride in dry ether, and then treat it with acid, so it will turn to primary alcohol. Then I'm going to treat my primary alcohol with the oxidizing agent, the acidified potassium dichromate. Then the primary alcohol, by doing distillation, I can get my aldehyde out. Okay, so remember, carboxylic acid will not be able to make aldehyde directly. Okay, so let's go through those examples together. So first, we have this benzoic acid. So remember, if you are given the question, so make sure you use a highlighter to highlight or circle the part that may undergo the reaction. So here we have the acid part. Maybe I use a different color. Okay, this part. So after the reaction, with lithium aluminium hydride in dry ether then treated with acid, it should undergo reduction reaction and go back to primary alcohol. So the rest of the carbon chain will stay the same. So let's draw it out first. Okay, so the benzyl part stay the same. However, the C double bond O and OH group will change to alcohol, the hydroxyl group. Okay, so let's draw the OH group. And make sure you fill the rest with hydrogen. Or for this case, okay, you can draw the condensed structure as this. Okay, let's take a look at the second example. Second example, okay, we have this molecule. Again, we treat it with a strong reducing agent, lithium aluminium hydride. So remember, lithium aluminium hydride is a very strong reducing agent. So it can reduce aldehyde and also it can reduce carboxylic acid. So double check our molecule here. The molecule again has a COOH group. Okay, but here you need to also pay attention. It got this ketone group here. Okay, so ketone can also be reduced. Okay, ketone cannot be oxidized to carboxylic acid, but ketone can be reduced back to secondary alcohol. So when we treat this molecule with lithium aluminium hydride, both of these two parts I highlighted will undergo reduction reaction and give you a diol. Okay, so let's work out the structure for the product. So again, the rest of the carbon chain remain the same. Now let's fill in the hydroxyl group. First, the carbonyl highlighted in yellow will turn into a secondary alcohol, and then the orange part will again turn into a hydroxyl group. So the answer should be like this. Okay? Then the next one. Okay, for this one, again we got the same molecule. So again we highlight the functional group that may undergo any reaction. But here we have sodium borohydride as a reducing agent. And pay attention, sodium borohydride cannot reduce carboxylic acid. Right? So in this if we treat this molecule with sodium borohydride, the carboxylic acid part will not undergo any reaction with sodium borohydride. Only the ketone part, this carbonyl group, will be reduced to alcohol. Okay, so we can erase this part. It will not undergo any reaction with sodium borohydride. So the product we have from this reaction would be like this. So we draw the part that's unchanged, that stays unchanged. Okay, and then the carbonyl group is gonna be reduced back to the hydroxyl group. So we draw it like this. So, and please pay attention when you are drawing the hydroxyl group. Make sure this bond is pointing towards the oxygen, not the hydrogen. Okay. The last type of reaction that you need to learn for carboxylic acid is called esterification. Okay, so by reading the name, you should know this is a reaction that make esters. Okay, and here, and you need to pay attention, this reaction is a reversible reaction. So you should use the reversible sign to represent this kind of reaction. If we treat carboxylic acid with an alcohol together with concentrated sulfuric acid and heat under reflux, then it will undergo a reversible reaction to form ester and water. Take a look at the example here. On the left hand side we have the ethanoic acid. On the right hand side we have the methanol. So for this part, the ethanoic acid together with the methanol, you can see we will be able to remove one of the water from these two molecules so that it will join together as a ester, which is a methyl ethanoate. and also that's why we name esters as these. Okay, so because an ester actually formed by the combination of an alcohol, which is a methyl part, and then with a carboxylic acid, which is the ethanoate part. Okay, so let's take a look at some more examples. So the first example is actually the first one, but we're turning it into a chemical equation. So after the reaction, we're going to remove the water, this part. Sorry. So after the reaction, you're going to remove water, the part I highlighted, and then it will form these esters. So we will write like CH3COO-CH3 ester together with water. For the second example, actually I made a mistake here. On the left hand side, you can see it's a carboxylic acid, and here we also got a carboxylic acid. So this is not the example I want to show for esterification. So please change the left hand side one by erase the carbonyl group. Okay, so now we have the alcohol with the acid here. Okay, so now we need to highlight the parts, highlight the water that we're going to remove from these two molecules. So we're going to take away the OH group from the acid and then the hydrogen from the alcohol. And then we can combine the rest to draw the final product. So it should be CH3COO, and then we have the benzene ring here. Okay, and together we have water produced. Remember to fill in the condition, we need to treat it with concentrated sulfuric acid and then heat it on the reflux. And then the next example we have here. So we have this benzoic acid together with the alcohol here. Again, let's highlight the water we're going to remove. So we're going to remove the OH group from the acid and then the hydrogen from the alcohol. Let's combine the rest of the part. So we have the benzene ring and then a carbon double bond to O, and then bonded to O, and then the benzene ring again, together with water as a product. Okay, remember the condition: conc sulfuric acid, and then heat it on the reflux. Then the next one, this one, we only have one molecule, so how can we do that reaction? But please take a close look at this molecule. In one end of that molecule, we have the carboxylic acid functional group here. And the other end, we have this hydroxyl group here. So actually, we can remove water from this part. Again, let's use a highlighter pen to highlight the water molecule we're going to remove. And remember, for a single bond, we can rotate it. So we can actually rotate this bond and make it connected to this part. Okay, so let's try to draw the molecules. So the rest of the part will stay unchanged. And then we got this double bond O carbonyl group. And then remember, we're going to rotate this bond. Okay, so after the rotation, we should have our oxygen here. And then we have the ring formed at this part. We can double check the total number of carbon. So if we count after the benzene ring, we have one carbon, second carbon. So here we have the first carbon, second carbon. So we only rotate the bond, but we didn't miss out any carbon from the reaction. Okay, and remember we have water produced as well, and we need to have the conditions labeled clearly. So the same principle going to work for the second molecule here. So on one hand, we have this OH group. On the other hand, we have the CO double bond O OH group. So highlight the parts that we're going to remove. Okay, so how can we draw the final product? Okay, so remember we can rotate the single bond and we can check what's the cyclic molecule formed by labeling the carbons we have here. So this we count from this oxygen. So after this oxygen, we have 1 carbon, 2nd carbon, 3 carbon, 4, 5. Okay, so in principle, after the 5th carbon, it should bond with this oxygen here. Okay, so remember, we can rotate the molecule. Okay, so it's gonna form the ring like this. Okay, so let's start with O at this position. That's the 1st carbon. That's the 2nd carbon, 3rd carbon, 4th carbon, 5th carbon, and then back to the oxygen. Okay, and remember we have the C double bond O at this position, so make sure you also draw the double bond O here. That's the 5th carbon, and on the 5th carbon we have the C double bond O here. And remember, on the 1st carbon we also got a methyl group, so make sure you draw that as well. Okay, so it should be like this, and then water formed, and then the condition. Let's take a look at the checkpoint questions together. Please pause the video, attempt the 2 questions before you go through the explanation. Okay, so for question 1, we have an alcohol and a carboxylic acid that are heated in the presence of concentrated sulfuric acid on the reflux. The following compound is obtained. Which of the following combinations is correct? Okay, so take a look at this part. Let's use different color to represent the part from carboxylic acid and then the part from an alcohol. Okay, so the parts with carboxylic acid should be the one with the carbonyl. Okay, so it should be the part on the right hand side. And for the alcohol, it would provide the part with C single bond O, which should be the one I highlighted using orange. Okay, so let's name the 2 parts. So the alcohol part got 2 carbons in it, so it should be the ethanol. Okay, and for the carboxylic part, we have 3 carbons in it, so it should be propanoic acid. So the correct answer, we should choose B. Okay. And then move on to question 2. Question 2. Isoamide acetate is found naturally as a flavor. Okay, and we have these molecules here. So which of the following pairs of reagents can this be made? Again, let's use different colors to represent the parts that from the original alcohol and the parts from the original carboxylic acid. So the key to solve the question is which one is a C double bond O? So how can we find it out? Okay, so for example, we can take this carbon and let's examine whether this carbon is double bonded to this O or single bonded to this O. So first you can see on the left hand side we got the methyl group. Okay, and then we'll move on to this carbon. So this carbon should only have 1 bond to this carbon. So far it got 1 bond. If this carbon is single bonded to this oxygen, then this carbon will only form 2 bonds. So that's impossible. Okay, remember carbon should form in total 4 bonds. So this carbon should be double bonded to this oxygen and then single bonded to this oxygen. So this part, this is a carbonyl group, and this part should come from the carboxylic acid. So again, I will use yellow to represent the part from carboxylic acid. So the remaining part should come from the alcohol, so I use orange to highlight it. So let's try to name the two original molecules. So for the carboxylic acid, since it got 2 carbons, so we should name it as ethanoic acid. Okay, so we should choose from C and D. Now let's check, how should we name the alcohol part? Okay, so for the alcohol part, remember the alcohol should be placed at the position 1. Okay, so now let's label the carbon. 1, 2, 3. Remember, we need to label the longest carbon chain. Okay, so 4. So this part, the other methyl group would act as a branch. So for this one, the longest chain should be 4 carbons, so it should be butane 1O. And since we have another methyl group attached to the 3rd carbon, so we should name it as 3-methyl butane 1O. So the correct answer we should choose is C.